This video discusses end-of-arm tooling, or EOAT. Some common types of end-of-arm tooling are grippers, paint sprayers, and welders or welding tips. So the end-of-arm tooling has two basic possible functions. On the one hand, the end-of-arm tooling could hold a tool that is going to work on a part, or it can hold the part that some tool is going to work on. Okay, so like if it's a welder, right, the end-of-arm tooling is going to be the welding tip, and then it's going to be welding on a part or parts to weld the parts together. So in general, there are four different design characteristics that we use specifically for grippers, if we're looking at end-of-arm tooling being a gripper. And those are the capability to grip and release the object, to detect that the part has been gripped, okay, and of course we want to try to keep the weight of the tool as low as possible, and we want to maintain the grip of the object as we're moving. So when we're trying to build a gripper, these are four different characteristics that we would like to see. Now, I'm not saying that every gripper meets these. I'm just saying these are design characteristics that we would like to build in there. Long term, like if you're talking about a gripper especially, we want the end-of-arm tooling to be able to simulate the human hand and all the capabilities that you can do with the human hand, which of course is grasping things, but also sensing things and manipulating things. So if we're trying to classify different types of grippers, we want to look at the method that we're going to use to hold items, any special purpose toolings or sensors, and whether they have possibly multiple function capability. So here is a picture of a robot with a tool, and this tool here, let me just get a little pointer and point down to here. Alright, so here is the faceplate of the robot, and you can see that this tool is actually offset, so it's not like mounted directly in center of the robot. So what we have to do is we have to teach what we call the tool center point, or TCP. So the TCP is the tool center point. That's kind of the business point or the focal point of the tooling that we have on there. And basically what that does is it maps it back to the origin of the robot. So the origin of the robot is where the first axis, the center of the first axis here, and the center of the second axis, where these two cross, which would be kind of like right back in here somewhere, and where those two meet, that's called the origin of the world frame, and that's kind of the robot's home. And so what the TCP does is it uses what's called a tool frame to define how far we are away from the faceplate. Okay, so the faceplate is where we mount the tooling, and then the point in space, when we're trying to teach a point in space, that point in space is mapped from the tool center point to, or from the world center origin of the robot. So just looking at some basic grippers here. These are just standard finger grippers, but even with these we have two different types of closing motions. We could have a parallel closing motion, or we could have an angular closing motion. Now if you had an angular closing motion as shown in figure A here, that you might get like a pinching. You might have more pressure near the joint where it's actually closing at, where if you had parallel it would be more of an even pressure along the part. So if that is an issue, you may have to consider that. Now to activate these grippers or these toolings, we can either use pneumatic, which is very common, using some sort of air mechanism to activate it. We could use a hydraulic if it was trying to pick up something larger, like heavy steel beams or something like that. We might want to use hydraulics for the strength. They could simply be spring loaded, and so activated by, when you attach it, it trips a spring and opens or closes. Or they can be electrically activated. So most of your standard finger grippers or vacuum grippers, of course, are going to just use pneumatics, compressed air, to operate the grippers. Okay, some grippers might be closed by either a pneumatic or electric actuator, but then when you turn that actuator off, then there's a spring that will open it. And that can be a problem because, number one, if you lose power, then the spring is just going to pop it open and it could drop or throw that part. And so, obviously that could be dangerous. And also, just when you're trying to set the part down, when it springs open, it could cause the part to move in a direction that we really didn't want it to move. So if you're trying to center a part, three-fingered grippers are much better. The two-finger gripper cannot center the part. It could be off on one side, and you may not have a good grip on the actual part. So three fingers are actually probably the best for centering it, but four fingers can often center it also, depending on the shape of the part. Alright, so here's just some common grippers that these are angular grippers here. And just kind of showing you some of the stats when you're trying to find a part. So this is a three-finger gripper with an angular kind of movement here, but as you can see, you just put the fingers on there and it will center a part between the three fingers. So when you're purchasing a robot, you really can't forget about the end-of-arm tooling, because without end-of-arm tooling, the robot is really kind of useless. And so it's not uncommon for grippers to cost 4 or 8% of the total robot cost. And when you're talking about a robot that is, $40,000, so you're talking, 8%, or just say 10% of that would be $4,000 for the gripper. So just even some basic grippers can be very expensive. Alright, so let's talk about gripping force. So remember, one of those things was that when you pick it up and you start moving, you want to make sure that the part doesn't slide out or fall out as you're moving it, right? You're supposed to keep a hold of it. And so part of that is due to, or a large part of that is due to the friction of the part and the smoothness of the part. So here we have just a 2-finger gripper grabbing a part, and so we're going to be making contact with both fingers. So keep that in mind here as we look in at the calculations. So we have what's called a normal force. The normal force is the force that's applied by the fingers when they're squeezing the part. All right, but remember, like if you're going to be lifting this part straight up, gravity's pulling it down. So one of the things that we have to be concerned about is the smoothness of the surface of the part. So if we're going to pick up a part, we want that to be smooth. And so we have to look at the coefficient of friction. The coefficient of friction basically is a measurement of how smooth or how slippery the part might be. Alright, now this is the coefficient of friction is actually considered a unitless number that is always less than 1. And so here's a little chart showing the different types of material. And so you have steel on steel, aluminum on steel, copper on steel, down, right here in the center, actually, we have that value of 1 that we were talking about. So if you took rubber, so if you had like a rubber finger on your gripper and you tried to pick up a block of concrete, that's going to give you a coefficient of friction of 1, which is the best grip that you could effectively get. That if your coefficient of friction is a 1, then you're getting a good grip, right? Because rubber is kind of soft and doesn't slip much. Concrete is kind of porous or has really rough surface, and so you can really get a good grab. However, when you look at this chart, there's 2 terms here. There's a static coefficient of friction and a kinetic. The static term refers to when you're not actually moving the arm, so you're just holding the object, but you're not actually moving. When you actually try to move, your coefficient of friction is going to drop. So even though you may have a good grip when you're sitting there holding it, as you start moving, especially if you try to start moving the arm fast, then there's an increased chance that the part will fall out. And so as you can see here, like we have like ice on ice, right? So if you had like a frozen finger, if you had ice on your fingers of your robot and then you're trying to pick up ice, the static coefficient of friction is only 0.1 there, or 10% of rubber on concrete. But when we try to move, it drops all the way down to 0.03. Teflon is even worse, right? Teflon is really kind of a slick kind of material, so its coefficient of friction is very small. So when you're trying to pick up the part, you have to also consider this coefficient of friction here. All right. So this is a little equation here which we can use to kind of determine how much force do we have to apply to this object. So we have this object here in the middle that we want to pick up this object. And so we have a 2-finger gripper, so when we apply, we're going to get that normal force here between the 1 finger and the part, and the force on the other side, the normal force on the other side pushing this way. But we want to lift this straight up. Alright, so here's the equation that we have to use. So we have the normal force times that coefficient of friction. Alright, and in this problem I'm using the static coefficient because I'm not actually moving it. But if I try to move it, especially if I want to try to move fast, then I got to actually use the kinetic coefficient of friction. All right. So in this example here, I have a weight which is 10 pounds. So the weight is 10 pounds. I'm going to try to lift this piece, this 10 pounds, which means that I'm going to have a force. Now, since I've got two fingers, I can split that, right? I'm going to have force over here, and I'm going to have force over here. And so I really need basically 5 pounds of force on both sides pushing up to lift the part. But what that means is if we use the coefficient of friction of 0.2 and we have a 5-pound worth of force going up, but my normal force is going to have to be 25. So I'm going to have to be pressing in with 25 pounds of force to generate 5 pounds of force on each side to be able to lift this 10-pound weight. All right. And that's just basically to lift it slowly and then hold it in the air, not move it very fast. Then I'd have to use the coefficient of friction for the kinetic, out of the kinetic side of that table. Alright, so here's just a vacuum gripper. And if you remember, one of the things we were talking about was trying to make the gripper as light as possible. But when you look at this gripper, you can see that this gripper is actually extremely large along here. So there's significant weight here. Now, to be fair, we're trying to pick up 5 of these large tubs of detergent or whatever that we're picking up here. And so if they're full, they're going to probably be pretty heavy. So there's a lot of weight that this is lifting up. But to lift that weight, we're going to have a pretty heavy gripper. And so when you talk about the robot being able to pick something up, you have to consider that not only is it picking up these 5 tubs of detergent here, but it's also picking up the gripper. And so the overall weight or mass that this robot can move has to include the weight of the gripper. So you always have to remember that when you're speccing out your robot, you got to consider how much is the gripper piece going to weigh and how much is the objects that it's going to pick up. All right. So this particular robot is using vacuum suction cups basically underneath of the gripper here. We can't really see the suction cups in this, but it's using suction cups to pick those up. Here's kind of a different example where we have lots of different suction cups and we're picking up a whole bunch. It looks like 1, 2, 3, 4, 5, 5 or 6 boxes here. I guess it must be 6 boxes, 6 rows of boxes, and it looks like maybe 3 in the other direction. So about 18 boxes here simultaneously that we're trying to pick up. So we got a lot of different section vacuum grippers. So let's take a look at how these vacuum grippers work. A vacuum gripper works, and it's a little confusing here because what it actually does is it causes a vacuum, and then the lifting is actually done by the surrounding air. All right, so we know, like at sea level, if we consider that we're at sea level, we have the pressure. There's always air pressure. And unless you're living in a vacuum or in outer space or something, right, there's always air pressure. So we always have pressure pushing on us. But it's pushing on us from all directions simultaneously. And so 1 atmosphere, which is a unit of pressure, is equal to 14.7 pounds per square inch, which is another measurement of pressure here. Now, we also have something called absolute pressure and gauge pressure. All right, so when we talk about this 14.7 psi, that is based on the absolute pressure. So just general pressure, and then any added pressure above that. Okay, and then the gauge pressure is just the pressure above the atmospheric pressure. All right, so here's kind of a little chart trying to show you that. So absolute pressure is basically saying if you were in a total vacuum, which is actually really hard to produce a total vacuum. Normally when we talk about vacuums, we're actually talking about something simply less than the atmospheric pressure of 14.7. And so, it's almost impossible to generate a true 0 psi vacuum. But the absolute pressure here you can see on this chart is the total pressure from 0 psi up to whatever your pressure is. But when you're using a pressure gauge to measure it, you're actually only measuring the difference between the absolute pressure and that atmospheric pressure surrounding us. All right, so how does this work? Well, let's say that we had this plate, which is 9 square inches. And so if the plate is just sitting there on a counter or workbench or something, air pressure is pushing it down. Okay, air pressure is pushing it down and all around it. So we have 9 times 15. What they did here was they rounded the 14.7. So if we look back here, right, we know that atmospheric pressure is 14.7 psi. What they did in this slide was they rounded that up to 15 just to make life a little easier for the moment. So what they did was they rounded up 14.7 up to 15. That's why there's all these 15s here. So what they're saying is for every square inch of this 9 square inch plate, there's 15 pounds of pressure pushing down. That's just the atmospheric pressure, always there. So what we want to do to lift this, what we're going to do is we're going to come over here and we're going to put a vacuum in this center square. Okay, so in the center square we're going to put a vacuum. And so that means that since we have 9 square inches and there's 15 pounds pushing down everywhere, but inside of this center square we're going to push down, we're going to create a vacuum, and so it's not pushing down at that center point. And so if that's the case, we can actually lift 15 pounds. All right, so we can actually lift a 15-pound object. All right, so the way these things work is through something called the Venturi effect. All right, so what you do is you actually use compressed air. So you have a lot of air pressure. You don't have a vacuum, you actually have a lot of air pressure right here. And then here's our suction cup. So what we're going to do is inside of this hole here, we're going to push in a lot of compressed air. And what happens then is inside of that gripper, is a kind of a constrained neck area here. And so as we push this air through, so we're pushing air through from left to right, and when it gets down here, it gets compressed and has to move faster. And what that does is that causes the vacuum right here. And that's where we get that vacuum. Now, again, this vacuum is nowhere near 0 psi. It's simply less than the atmospheric pressure. So like in the example that I just did up here, this is assuming that we were actually able to create a perfect vacuum underneath of this center square inch section of this plate. But in reality, we're not going to get anywhere near that. So we wouldn't be able to lift a full 15 pounds. All right. Here's a schematic of an air valve. If you remember, we already talked about pneumatics and using valves. So this is a two-position valve. It has a solenoid. So right there you can see the solenoid on there, and then when you activate the solenoid, that allows the compressed air to flow through here. Here's your Venturi throat on there, and then this causes the vacuum over here. So we have compressed air coming in, and then that compressed air is just moving right through and just being blown out into the atmosphere, but it's causing a vacuum over here at this section. All right, and then when you release the solenoid, the voltage off of the solenoid, then your the spring on the other side of the valve here pushes it back and shuts off the air. So when we're trying to get a lifting force, okay, as we increase the suction cup size, we can obviously increase how much coverage and how much vacuum we're creating, and therefore lift more. So that's all this chart's showing. All right. We can also use magnetic grippers. Okay, magnetic grippers are good if you're trying to pick up some sort of ferromagnetic material, such as a soft iron, something like that. So what we do is we have an iron core with copper wire wrapped around it, and when we apply a voltage on that copper wire, we get current flow, and that generates a magnetic field. That's called the Faraday effect. The current through the wire generates a magnetic field. By wrapping many loops around it, we magnify the amount of that magnetic field. All right, here's an example of some rubber fingers that work by basically inflating them. So if you inflate them, you can get them to actually move and kind of move almost like an actual human finger. Not quite, but along that shape. All right, so this here gripper is called a mandrel. And the idea here is what we can do is we push the gripper down inside of a cylinder, and then we have a rubber diaphragm, and we fill the rubber diaphragm with air, and it expands out and makes contact with this cylinder, and then we can lift this up. And this gives you number one, you're using a rubber diaphragm, so you're going to have pretty good friction with that, and you have a 360 degree grab around this cylinder, and so this actually gives you a really good hold. All right, now the opposite of that is what's called a pin gripper. In this case, we're trying to pick up the pin, and we're putting the cylinder down over top of the pin, and then again we got the rubber diaphragm in here, and we fill that full of air, and it makes contact all the way around this cylinder on this part, and again it gives a really nice grip. So when you're trying to calculate your gripping force there, you need to remember that the area, since it's a circular area, we have to look at the circumference, which is 2 times pi times the radius of the cylinder, and then multiply that times the height, and that'll give us the total contact area that we're grabbing. All right, now another term that we have to consider when we're trying to pick up parts is something called compliance. Compliance talks about, well, if I'm going to move down and pick up something, what happens if I'm not perfectly aligned? So like when we're coming down here and we're trying to put this cylinder over top of this pin sticking up. Well, what happens if we're off a little bit? Well, if you look at the drawing here, down here at the tip, so when it first starts going in, you can see there's a little angle here, or chamfer. And also on the part itself, it has a chamfer. And the idea there is that makes it a little bit easier. So if you're off just a little bit as you're coming down, that'll help allow it to shift a little bit so that it can move down and come across the part like it should. And that's what we're talking about, compliance. So using a chamfer like that is considered passive compliance. All right, so you can have very high compliance, which means that the tool has a lot of movement in it, so it has a lot of flexibility. A lot of times it's like vacuum grippers, especially, they're made out of a rubber material that's going to be springy, and so they tend to have quite a bit of compliance. If you're using metal finger grippers, they tend to have very small, very low compliance because they're real stiff and they don't move. So you got to have your parts lined up within the gripper very nicely. Now, here is a couple of different types of issues that we can run into. So the part is that we want to come straight down into this hole with this part, but if it's not lining up quite correctly, we could run into two things. Number one, we could be off left or right, and the other is that we may need to rotate. See, now there's a chamfer on here. If you look at this part, right, you see that part has been chamfered right along that hole, so that if you're off a little bit, it gives it the ability to slide down in. The only problem is when it starts sliding down, now it might actually go in at an angle. So now it's not going straight down because it gave and it bent over a little bit. So if we use something called active, well, let me talk about passive compliance first. So here is kind of a similar picture to what we were just looking at. And this is a passive compliance type device. And what this does is it has these shear pads here, so that when we come down, you can see here it's a little bit off to the side. And so if it starts sliding, it might try to like bend and end up going at an angle, right? So it might actually try to, it's trying to come down here, but it's not quite going to make it because it's not lined up properly. But if we could rotate it at an angle, right? So if we could rotate this, well, that seems like that might be good, but if that's the case, now it's coming in here at an angle and not going to be straight down. So what this particular gripper allows us to do is it gives us both rotational compliance, so it'll let it rotate, but then it also will let it shift over. So you can see here, hopefully, let me grab my gripper here, come on. All right, so you can see here that this particular gripper has been designed so that it can it can allow it to sort of rotate over and in, but then shift laterally so that the part actually ends up coming straight down as it should. All right, so that's passive compliance. So you have to build your gripper to the allow it to line up if your program is not quite properly lined up. Now, active compliance, now on the other hand, uses sensors. So what it does is we have to mount sensors on here so that we can tell when it starts hitting that part that there's forces or torques being applied. So this is kind of active compliance is pretty expensive because these sorts of three-dimensional force and torque sensors get kind of expensive. And so, but if you need it, then they are available. And what it can do then is it can feed back into the controller and tell the controller what direction to move to line it up. And that's why it's active. So you have a sensor, and the sensor is recording forces as you're trying to force the part down in there, and it's not quite lined up. And then you feed back these torques, torques in the X, Y, or Z direction, and also any forces in the X, Y, Z direction, and then the controller will have to make adjustments to just move the arm till it does line up. Alright, so here we're going to discuss the wrist interface. When you talk about the wrist, that's the part basically where we're mounting to the faceplate, so that's kind of our mounting point. And of course there's a mechanical interface there that you're going to bolt your gripper to the faceplate. Alright, but sometimes on certain applications we want to be able to change the tool very, very quickly. And so there's a lot of different mechanical sort of designs that have been made to allow the robot to change its gripper without a human being present to go in and unscrew the old gripper and screw in the other gripper or whatever the need might be. We also have to have an electrical interface on the robot so that we can activate the control and also any sensors, if we're going to have sensors on our grippers to kind of detect whether the part's actually there or not. Right. Pneumatic interfaces are very nice because one reason is that they have a quick break and reconnect. So it's pretty easy to connect or disconnect the air hose. Number two, if it leaks a little bit, it's not going to cause damage like a hydraulic line leak would. And so, and a lot of times, like I say, we're, in a lot of newer applications especially, we're looking for very rapid tool changes for it to be able to change our various tooling. Now, we also have to consider collision systems. So as we're going down to pick something up, if we're not in line or an object's in the way, what happens? All right, and so one of the common things that we do is we build in something called a breakable link. Now, you've probably heard the old adage that, a chain is only as strong as its weakest link. Well, the point is that we build in a weak link so that it'll, if something does happen, it can break that link and not cause too much damage. So the idea is that we have something that's relatively cheap and easy to replace to prevent from damaging something that's much more expensive and going to cause a lot more downtime and a lot more cost to replace or repair. We can also there's a lot a lot of the newer robots actually use a lot of various software collision detection techniques to prevent any danger. All right, so or we can do some other thing like a spring or a pneumatic breakaway, so that if a collision or something was to happen, again, the pneumatic or a springs type of thing would just allow it to break away and minimize any damage.